Welcome to our presentation of our NeurIPS2024 paper, Newton losses, using curvature information for learning with differentiable algorithms. I am Felix Petersen, and this is joint work with my collaborators Christian Borgelt, Tobias Sutter, Hilde Kuehne, Oliver Deussen, and Stefano Ermon. In this work, we enhance training with differentiable algorithms, applying second-order optimization to loss functions that incorporate differentiable algorithms and which were previously a bottleneck in training, while we continue to train the neural network with gradient descent. Typically, when training a neural network with a standard loss function, training the neural network is the hard component. Typically, it is trivial to find the minimum of the loss in terms of the input of the loss. However, in our setting, where the loss entails a differentiable algorithm, optimizing the neural network is easy compared to the algorithmic loss. The algorithmic loss is often non-convex, hard to optimize, exhibiting vanishing as well as exploding gradients, and thus the loss is the optimization bottleneck. Thus, we consider splitting between the neural network and the loss. Conventionally, one optimizes the neural network parameters theta, one optimization step at a time, computing the gradients with respect to the loss L. Instead, we conceptually propose splitting the step into two steps. First, we use an optimization step on the neural network outputs, that is, on the loss inputs. We call the result of the step Z star. Then, we use a squared loss to optimize the neural network to minimize the distance between the currently predicted output and our proxy goal Z star, as evaluating the loss is usually cheap, and even second-order optimization on the loss is still cheap and becomes only expensive when second-order optimization would be applied to a neural network. We propose step 1 to be Newton's method, while step 2 remains stochastic gradient descent. Equipped with the idea, we can transform the loss L into a Newton loss L star, which simplifies the idea by expressing the step on Z in closed form, thus requiring only a single optimization step in modern deep learning frameworks. Here, we require a Hessian, but sometimes it's not available, so we propose an extension that only requires the empirical Fisher. Now, let's discuss how we can implement Newton losses and start with a Hessian formulation. After the setup of the model, loss and optimizer, we as usual propagate our input through our neural network. Next, we compute the gradient and Hessian of our loss function with respect to the prediction y. This lets us compute Z star in closed form via a Tikhonov regularized Newton step. Finally, we can use an MSE loss between the prediction y and the new goal Z star and backward on that loss. Next, let's discuss the empirical Fisher extension. Here we found a very simple strategy for integration into deep learning frameworks via our so-called inject Fisher custom autograd function. Integrating Newton losses here only requires calling y equals inject Fisher of y between applying the neural network and the loss function, and no further modification of the training pipeline. Internally, inject Fisher has a forward that is just the identity. Only during the backward, the inject Fisher function modifies the gradient in a way that is equivalent to using the empirical Fisher variant of Newton losses. Here, in the backward, we first compute the empirical Fisher, which only requires the gradients, which are, of course, in the backward already available. Then, we modify the input gradient, which would conventionally just be g, as this is an identity in the forward. Here, we multiply g by the inverse of the Tikhonov regularized empirical Fisher. Overwriting this gradient makes it equivalent to the Fisher-Newton loss. Note that these inverses are not expensive, as the output dimensionalities of neural networks are usually very small. Proceeding to our experiments, let's start with our ranking losses experiment. We used a 4-digit MNIST sorting benchmark with a range of differentiable sorting and ranking algorithms in our loss function. In the results, we can see that Newton losses consistently improve over the baselines for neural sort, soft sort, as well as logistic and Cauchy differentiable sorting networks. We see that the Hessian Newton loss performs better than the Fisher one, but the Fisher is still an improvement. We can see larger improvements for worse differentiable algorithms and smaller improvements for already better algorithms. This is because our method has a larger effect when the optimization of the loss is harder. Next, on the Warcraft shortest path benchmark, which benchmarks differentiable shortest path algorithms, we can observe similar effects. Newton losses consistently improves over the baselines, with greater improvements for worse underlying methods, but still showing improvements even for the best differentiable algorithms. Thanks so much for watching. We are going to release the code on GitHub and we are looking forward to seeing you at our poster session.